Hi everyone, my name is Michael Wu from National Taiwan University. My topic for DML talk is sensing, tracking, and secure communication with artificial electromagnetic materials.
What exactly is the so-called artificial electromagnetic materials or metamaterials? Basically, they have unique properties and applications that stem from their ability to manipulate electromagnetic waves or EM waves in ways not found in nature materials. For instance, one of the earliest examples for metamaterials is probably the so-called Lycurgus cup located in British Museum. The interesting property for this cup is if you shine light from different directions, it will appear different color. For instance, if you illuminate the light from the inside of the cup, it will appear red color. On the other hand, if you shine light from the outside of the cup, it will appear green color. And this is because the cup is made of ruby glass, which contains a lot of silver particles, which will result in this frequency selective property. On the other hand, another famous example is probably this so-called mental cloaking in Harry Potter. In Harry Potter, if you remember, he can just put on a cloak and then he will appear invisible. And this is also another interesting property for metamaterial due to their ability to manipulate the EM wave. When the EM wave is traveling inside a certain material, the characteristic can be usually characterized by the material's dielectric property and magnetic property. Dielectric property can be characterized by so-called permittivity or dielectric constant epsilon, shown here. And then the permeability is usually characterized as magnetic property. These two constants in nature are usually positive. However, when we properly design some periodic pattern on top of these materials, we can alter these properties. In some cases, we can manipulate this both constant to be effective constants such that in some frequency regime, these two constants can become negative values. This interesting property cannot be usually found in nature, and which are usually artificially engineered materials. So therefore, we call it metamaterials. Or when a EM wave is propagating in some material, we know its electric field and magnetic field can be related through the very well-known Maxwell's equations. In this case, you see changing electric field will result in changing magnetic field, and changing magnetic field will result in changing electric field. In addition, the propagation constant beta is a function of dielectric constant epsilon and permeability mu. In this case, the phase constant beta can be used to characterize how much phase per unit length the wave will travel. On the other hand, when we look at a transmission line model, the transmission line unit cell will contain a series inductance L and shunt capacitance C. In this case, the characteristics can be characterized by so-called telegrapher's equations, where the voltage wave and current wave are coupled with each other through these two equations. Taking a closer look, if we map electric field to voltage and magnetic field to current, also permeability to inductance and dielectric constant to capacitance, we can see how analogous these two equations are related to each other. Having said so, if we look at a conventional transmission line that contains a series L and shunt C, we can then derive its propagation constant, which is equal to the angular velocity multiplied by the square root of LC. In this case, since all the quantities are positive, we will always have a positive beta. And if you plot the dispersion diagram, which is showing the relation of omega and beta, they will have a linear relationship. In addition, when we look at the phase velocity, which is the velocity of a constant phase point, in a lot of cases, the phase velocity can be used to characterize the velocity of EM wave. Usually, it will be the speed of light of the material. On the other hand, for metamaterial, this might not be always the case, where we will talk about it shortly. Because phase velocity is a positive quantity for conventional transmission line, we can then use our right hand to characterize this characteristic. If we do E cross H, use our right hand, we will have our thumb pointing towards the phase velocity direction, which indicates the propagation direction. On the other hand, if we flip the two electric components, C and L, now we have a series C and shunt L, we will have a negative propagation constant beta, because in this case, beta will be equal to negative 1 over omega square root of LC. And therefore, we will have a negative first velocity, which means the propagation direction will be the opposite of a conventional right-handed transmission line. And this will open up a lot of interesting applications which cannot usually be done using the conventional transmission line. We will talk about this shortly in the later part of the talk. On the other hand, if we want to realize a pure left-handed transmission line containing a series C and shunt L, we will inevitably always have parasitics series L and shunt C come into play. So this will result in so-called composite right-left-handed transmission line, or CRLH transmission line, that will have the effect of all these four circuit elements, namely right-handed L, left-handed C, right-handed C, and left-handed L. This unit cell, CRH unit cell, can be used to represent the so-called CRLH transmission line. In addition, if we look at the dispersion diagram, which will again tell us the relation of the propagation constant and the frequency, also the relation of phase velocity and its direction, we can see that for a conventional right-handed transmission line, beta will always be positive, and it will lie in this so-called guiding wave region where the wave will not propagate. On the other hand, if we plot the dispersion diagram of a CRH transmission line, we can see the curve will come across all the four regions, namely left-handed guided wave region, left-handed radiation region, right-handed radiation region, and right-handed guided wave region. Because the CRH dispersion curve can come across both left-handed radiation region and right-handed radiation region, this can result in a fast wave propagation and also leaky wave propagation for antenna application. In addition, if we operate the CRLH transmission line in its balanced condition, we can close the band gap to form a very smooth transition across both left-handed regime and right-handed regime, which will be useful for leaky wave radiation. By operating the CRLH transmission line in its radiation regime, we can then utilize it as a leaky wave antenna. And because beta in the CRLH transmission line can be negative, 0, or positive, so therefore we are able to control its main beam direction. For instance, in this case, if we inject the power from one of the port of the antenna, depending on the frequency, if it's operated in the left-handed regime, the beam will go to the backward direction. If it operates at the center frequency where beta is equal to 0, then the main beam will go to the broadside. On the other hand, if the beta is positive and we operate it in the right-handed region, then the beam will go to forward direction. This simple frequency-dependent beam scanning capability can allow us to do main beam manipulation, which is very useful in particularly doing radar sensing detection. So then we design a CRLH leaky wave antenna at the 24 gigahertz range. As you can see here, when we scan the frequency from lower frequency to higher frequency, we can see the main beam actually will change. And we connect this leaky wave antenna at 24 gigahertz to a radar sensor chip. We can form a frequency-dependent radar sensor, which does not need any mechanical scanning or phase shifter to steer the beam. By utilizing the frequency scanning capability of the metamaterial leaky wave antenna, we are able to create a very simple radar sensor that allows us to detect multiple targets' vital sign information out of it. For instance, we have target A and target B sitting in front of the radar sensor. By simply changing the center frequency of the radar sensor, we are able to change our main beam to point towards either target A or target B. If we operate in a lower frequency, then we will obtain target B's information, including its breathing rate and heartbeat rate. On the other hand, if we change the frequency to 26.3 gigahertz, we're able to obtain information for target A.